Today we're going to be looking at a new bootloader that I've developed at Broadwell Consulting Incorporated for the PIC16F15214. This was a personal project that I undertook for my own entertainment and education, and it is available as an open source MIT licensed project at github.com/Broadwell Consulting Incorporated /bootloader PIC16F15214. There's a link in the comments below. If you go into this repository, you'll find three folders. One is the bootloader itself, which is C code, primarily a little bit of assembly. That is the bootloader. There is an application written in C#, quick and dirty application that implements the downloading method, as well as the ability to read and fill in an Intel hex file, and a sample application that shows you how to offset the application into the proper memory range, as well as include jump stubs for the reset vector and interrupt vector, which is very important. There's also an example of how I implemented jump back to the app using the overflow reset vector. The hardware for this project is quite simple. We have our 8-pin microchip PIC in here. That's attached via a harness. 5 of the pins go off to the microchip PIC Kit 4, which will be doing our programming. This device right here is a UART to USB converter. That'll show up as a COM port on our PC. We have 2 lines, the gray and the orange, tied up to the TX and RX on the PIC's UART. And this guy is also doing 5 volt to 3.3 volt conversion, although this particular PIC is 5 volt capable. I also have my SALE logic analyzer hooked up to the TX and RX pins that we will be using to indicate, to demonstrate some of the communications that goes back and forth. So let's take a look real quick at the code. There are 2 embedded projects that we're interested in. By far the most interesting one is the bootloader. The bootloader exists as 2 files that started out as microchip code generator files that I flattened into a single main file, primarily to get rid of call instructions. I wanted this to take up as little space as possible. As such, I have also compiled this using the optimization for small. That is a function that requires the pro level compiler, which has a cost associated with it. There's no reason you can't compile this bootloader using the -02, which is the highest free level of optimization, but the code will get larger and you will need to move the reset vectors to accommodate the extra flash space that you will need. So if you look through here, there's a variety of documentation that I've written at the beginning. The bootloader, there's a number of different ways that you can choose to stay in a bootloader. For this particular bootloader, we come in to main. We do setup on the various pins that we need. And then we go to, are we going to stay in the bootloader or are we going to make a jump to app? And so this bootload required function decides if we stay in the bootloader. There's a number of criteria for us to stay in the bootloader that are listed here. Is the first location in the application space unprogrammed? 3FFF. If so, then that means that we don't have an app, we need to stay in the bootloader. This bootloader requires that the last word in application space be programmed to the magic value I picked, 14B7. If that's not the case, then it assumes that the prior programming did not complete all the way through and will not make the jump to app. If the last reset was caused by a hardware stack overflow, that's the indicator that I'm using from the application that we want to stay in boot in order to download a new application. This may or may not work for you. If you wanted to implement some kind of a flash EEPROM emulation to stay in boot, or if you had, a magic pin that you wanted to use or whatever, you can modify the code. I also wanted an external way to force us to stay into the bootloader. Well, since the 16F15214 only has 6 I/O pins, counting the reset pin, I didn't want to waste one on a stay in boot pin. So I came up with the special criteria. If we powered the system at between 1.8 and 2.2 volts, which is within the operating programming range, then we will stay in boot. The nominal voltage for this project will be either 3.3 volts or 5 volts, so 2.2 or lower would be a special case. Again, if this doesn't work for you, come up with your own scheme and change it. So we walked through the bootloader required. If the last address isn't the special value, we say whether the low or high byte of that word is not correct and pass that back up. These values will get passed out via the serial port during the initialization so that we know if we're staying in boot, why are we staying in boot? That'll be potentially useful for debugging. If the first vector is not programmed, if the first word of application space is not programmed, we hand back an F. If we determine that there was a stack overflow indicating that we should stay in boot, we got an S. And if the voltage is less than 2.2 volts, we return a V. Note that we check the voltage twice with a 100 millisecond delay. This is because if this bootloader is used on a system where the VDD has a slow ramp rate, it's possible that we may start out at 2.2 on our way up to 3.3, yet see a single sample early as being within that threshold. So we check it twice. If it comes back twice at 2.2, 100 milliseconds apart, then we stay in boot. If this doesn't work for you, again, feel free to customize it. It's open source software. Once we have made the decision that we need to stay in boot, then we run the bootloader. The bootloader does a number of things. First, it sends out a string to the serial port that says I'm in boot, along with a byte that says why I stayed in boot. Then it sits in a busy loop looking for another 32-bit magic word, 52A34DF6. Under those circumstances, then it says, okay, somebody wants me to go into the bootloader. This wasn't an errant entry into the bootloader, and the odds are 4 billion to 1 that somebody actually wants me to do this, that this isn't a fluke. At which point it will send out an E command saying, hey, I'm starting an erase. It will erase the entire application space. After that completes, it takes a long time being a fraction of a second, but still in computer terms, a long time. It sends out a W, which tells the application, send me the first line of flash that I need to program. And this bootloader pushes almost all the intelligence off onto the PC side. The PC needs to interpret the hex file. It needs to fill it. It needs to send the entire image in order with breaks at the appropriate point for the flash lines to be programmed. So it is not versatile, but the trade-off of that is that it is very small compared to for instance, the default bootloader that's generated by Microchip Code Comparator. It is not flexible, but it is small. So we go through here and we walk through and read bytes, write them into the shadow registers for the flash. When we get to a 32-bit word boundary, then we initiate a write. And we do that over and over and over again until we get to the magic value, which is 1,000 words. At which point we send an R out the UART, and our verification of proper programming falls entirely on the PC. Since we have such a small amount of flash here, about 7K, we simply read it all back out the serial port and let the application on the other side verify that each of the bytes were programmed correctly. Then we go into a while one loop. In order to get out of this bootloader, you have to reset or power cycle the microcontroller. At the top of the bootloader in main.c, you'll find a few important items. One is the new reset vector, and that's for your application. Where is your reset vector going to be placed? Normally for this chip, it's at 0, but that has to point into the bootloader. When you build an application, you will want to have the reset vector at a fixed address. For me, that's 140. If I build the code, I'm well within my 140. If you recompile this using -000102 instead of -OS, perhaps because you don't want to pay for the pro version of the compiler, then your code is going to get bigger. You're going to have to change this value. Below the reset vector, there's an interrupt vector, which is how we get to our interrupts. The bootloader doesn't use interrupts, but because the bootloader vector is within the bootloader, because the interrupt vector is within the bootloader space, we need to put something there. And essentially what we've got is something that just jumps to the new interrupt vector. So your interrupt vectors for your application are going to be, in my case, at 144. In your case, if you change this, at something else. So now let's take a quick look at the application. Our application has a number of files in it. We have main. This looks an awful lot just like a normal main function. Actually, you can't tell the difference. It's generated out of MCC, and I did a little bit of modification. The sample application uses interrupts, which is important for us to prove out that it works. So let's take a quick look. So we can use our debugger and debug this. Made a mistake. Over here, when you have more than one project loaded, I was just loading my bootloader. That's not what I want to have happen. I want to load the application directly. So I need to go over here, right click, and say set as main project for my application. So let's debug this guy. Okay, so we were running. And if you look at the serial port that's connected to this, it is dumping out a constant hello world. Let's do a quick reset on this guy, and let's look at our reset vector. If we look in the .s file, there's a few things in here that are important. First, we use a PIC16F15214, an org, and a define word statement that set the magic number that we talked about. This goes all the way at the end of flash. Next, we need a reset stub. And what that does is it jumps from 0 up to 140, which is the beginning of our application. The bootloader normally does this for us, but if we want to be able to load the app without using the bootloader, then we'll do that. We can also see that we put the same interrupt jump vector in there as before. We'll put a breakpoint on that as well. So let's do a reset. Go. And we can see the very first thing that we do is we stop at 0. So now if we do a step, we jump up. This is some of the behind the scenes code that exists before you get to your C code. It's initializing variables and running through stuff like that. If we come over here to the beginning of our main, put a breakpoint here, we get in there. So that's very good. Now if we hit go, the first time we hit an interrupt, it comes down here at location 4, which normally is where the vector or the interrupt handler itself is located. But in this case, we have a go-to. This matches the one that's in the bootloader. And so it jumps up here, and we do get to the proper interrupt space. So that's very good. Again, if you change the location of your application's top due to changing the bootloader or changing the optimization, you'll have to change these values to match whatever is in the bootloader. So we hit go, and everything works great. We're dumping out hello world. All Microchip MPLab projects need to have their config bits set. When we generated our code over here in the bootloader, MCC generated config bytes for me, config words, and I want to copy those from here to the application. You cannot have separate config words for your application and your bootloader. So these things sometimes play against each other. Like, for instance, you may want to have a permanently enabled watchdog, or you may want to permanently lock the PPS. Well, that may not work for your bootloader, so you may have to come to some level of compromise. But you want to have the same set of config bits in your application and your bootloader. Otherwise, the two programs are going to behave differently. One of the things that we have is the ability to jump to boot. And that's important if the application says that we want to be able to download a new application. The way that I implemented it for this particular bootloader, I know that the actual application I'm going to be building has a very shallow stack depth, so we should never even get close to exhausting our stack. I'm not using recursion, and I have very few calls. So what we're going to do to jump to app is we're going to set the stack pointer to the top of its capability. Then we're going to make one more function call to this dummy function up here. I put something in there just to so it would have a volatile variable so it wouldn't optimize this function out. And it calls up to the dummy function. At this point, we will get a stack reset. We'll go back into the bootloader. The bootloader can see that this was a stack reset, a stack overflow reset, and it will stay in boot so that we can download a new program. Let's take a look real quick and actually download our bootloader and see the thing run. Oh, one other thing that we should talk about. Inside the application, you're going to need to offset the application in order to have the proper spacing. And in order to do that, you go into the linker, additional options, code offset, 0x140. Again, this is another magic number that needs to match wherever you're starting your application. If this number doesn't match up with what's in the assembly jump go-to instructions, you're going to have problems. The other thing you're going to want to do is under memory model, the linker may try to put something in the magic location that we use for the flash finished programming indicator word. And so under ROM ranges, I'm going to put a -FFF, -FFF. And what that says is from word FFF to word FFF, the linker is not allowed to use that location. So if it wanted to put something there, it won't, which leaves that word for me to explicitly fill in using this org address right here. And this is in bytes, the other one was in words. If I don't do this, you may get an error that says you have conflicting values. That's because you tried to put something in here explicitly, and the linker, based on the ranges it had, also tried to put some data in there. And so you have a conflict. To avoid that, you add that -FFF, -FFF to the ROM memory ranges. So let's go ahead and run our bootloader now. So now I'm going to program our bootloader into the chip. I'm going to close TerraTerm so that we can use the port otherwise. Open the quick and dirty app I used to download. Open COM8. Select a file that we're going to download. Here's our hex file. And we can see it. It's doing what it needs to do. Now at this point, we'll close that. And we can see when we went into boot, it said ebootl. That's actually to work with, so it looks like a command from another application that I'm working on. You could make it say whatever you wanted. But it said eboot, and the L indicates that the low byte of the magic word did not show programmed, so the bootloader decided to say in the bootloader, which it should. Now at this point, we have a loaded application. I'm going to power cycle the chip, which is how we get out of our bootloader. Connect up with TerraTerm. And we are running our Hello World app. We said before that we can jump to the app by using this function in the application The jump to app happens if we send it a J. So let's do that now. And you can say, okay, it did that. It went through its reset. The bootloader recognized that. And it says, I'm staying in boot because I had a stack overflow. So now at this point, we could either power cycle to jump out of boot, or we could do another download. Let's do another download. Only this time, let's take a look at what's happening on the logic analyzer. Now let's take a look on a logic analyzer as we do the same download. And we can see in here the same set of steps. What we have coming in, at some point in the past, the bootloader announced itself with its startup sequence. And we can see that we send a 52, A3, 4D, F6. That's just our magic, let's start bootloading 32-bit key, at which point the bootloader responds with a lowercase e, indicating that it is erasing. And then at that point, it takes it, we can see about 300 milliseconds to do the erase, at which point it indicates back to the application that I'm ready to write. W, send me some data. Windows screws around for a few milliseconds, then sends it the first 64 bytes of data. The bootloader programs that in, sends another W saying I'm ready for the next word, the next line of words. And it continues like that. You can see back and forth and back and forth and back and forth until the entire space has been programmed. At which point we get to the end, and the bootloader sends a final W indicating the end of that, and then sends an R saying I'm getting ready to read back the entire application space to you. And at that point then, as fast as it can, it just streams out the entire application area. If we go in here, we can see that a lot of these bytes near the end are 255.3F, 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 which is unprogrammed, which means that the application didn't come close to taking up the final space. It gets to the end, and there's no more interaction between the bootloader or the application. It's up to the PC application. It's up to the PC application to determine if the verification was successful or not. If not, it should alert the user and say, hey, somewhere in the middle we had a corrupted byte. This could happen, and the bootloader may not notice it. The bootloader only looks at the first couple bytes, the last couple bytes, and that's about it. So verification of every individual byte through this area is left to the readback to the application on the PC side. I hope you've enjoyed this tutorial on the bootloader that I wrote. I hope that you can take this code and use it for something useful. If you have questions, you can leave them in the comments below. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting.